In this lecture, we are going to look at statistical testing in code. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. To start, we're going to import the jark-bera test and the normal test from scipy.stats. These are two functions that test for normality and return both the test statistic and the p-value. You're encouraged to check out the documentation for these functions if you want to learn more about the arguments and their return values. So first we call the function jark-bera on our values array. If you recall, this array is just an array of Starbucks returns. What we see from this is that the test statistic is very large, and accordingly, the p-value is very small. In fact, it's so small that it gets rounded down to 0. Therefore, we reject the null hypothesis that this data comes from a normal distribution. Another test we can look at is the normal test. Interestingly, this test is not named after a person, but you can check out the documentation in SciPy if you want to see which statisticians inspired this test. If we look at the results, we can see that they're encapsulated in a normal test result tuple, but the two values it contains are what we expect to see. What we see is that the test statistic is again very large, and the p-value is again very small, about 3 times 10 to the power minus 38. Again, we reject the null hypothesis that this data comes from the normal distribution. Note that we can try these on the log returns as well. So in the next few lines, I'm calling the same functions, but I'm calling them directly on the log return series stored in our data frame. Note that we have to drop the NA values, otherwise they might be considered part of the data. If we look at the results, we again confirm that the log returns are not normally distributed. Next, we're going to try the Kolmogorov-Smirnov test. Now, although we could try this with the normal distribution, I think we're pretty convinced at this point that our data is not normal. So we're going to use the t-distribution instead, since we established that this might be a decent fit. Note that in order for the KS test to work on an arbitrary distribution, we have to pass in the CDF as an argument. Now, recall that SciPy functions expect its probability functions to not have any extra parameters other than the data. That's why we had problems earlier with the t-distribution, since it has a required parameter for the degrees of freedom. Therefore, we're going to have to create our own CDF function. But first, we need to actually determine the parameters of this t-distribution. Luckily, we already know how to do that using the function t.fit. Next, we define our CDF function as follows. It simply calls t.cdf, but passing in the degrees of freedom, location, and scale parameters that best fit our data. Finally, we call kstest, passing in our data and our CDF. The result is that we get a very small test statistic and a very large p-value. This indicates that we cannot reject the null hypothesis, and in fact, we're not even close. In the next block of code, we do the same test, but on the log returns. Again, we obtain a similar result. We cannot reject the null hypothesis that the data comes from the t-distribution. Next, we're going to switch gears a bit and do a one-sample t-test. So now we are no longer testing what distribution the data comes from, but checking how the data compares to some value. So for this, all we need to do is call the function t-test_onesamp, passing in the data and the mean for the null hypothesis. For us, that's going to be 0. If we look at the results, we get a p-value of 0.085. In fact, this is pretty close to our significance threshold, but we still fail to reject the null hypothesis. If we check the same test for the log returns, we get an even higher p-value. Now, it's important to remember that these are two-sided tests. As an exercise, you might want to try to figure out what the p-value should be for the one-sided test. Now, because that test didn't show significance, I wanted to try another stock, this time 3M, which has the ticker MMM. So first, I filter all the rows where the name is equal to MMM and assign that to the variable MMM. Next, we plot the data so you know what it looks like. As you can see, there's a pretty clear trend upward. Next, I do the usual calculations to calculate the return and the log return. Next, I calculate the mean and standard deviation for the return. Note again how close this is to 0. But remember, this does not imply that the expected return can simply be rounded to 0. The scale in your mind is different from the scale of financial returns. Recall that when we looked at the prices, we saw that they generally trended upwards. Whether or not this data is significantly greater than 0 depends on the number of data points we have, as well as its variance. Next, we draw a histogram of our returns. Looking at this, your intuition might tell you that this is simply a bell curve centered around 0. That's why I don't like intuition. Intuition is wrong, and that's why we need math. Next, we go through pretty much all the same exercises that we did previously. The next step is to calculate the 95% confidence interval. This is the same equation as before, so I'm not going to review it again. The next step is to plot our confidence interval along with the 0 line. At this point, you now know what the 95% confidence interval represents with respect to this 0 line. We've actually done a z-test. In this case, the 95% confidence interval does not include 0. Next, we run the t-test on both the returns and log returns. This time, we get a p-value of about 0.01 in both cases, and therefore, we reject the null hypothesis that these returns come from a distribution with true mean 0.